let's review what we've done by putting it all in a general setting. So the general setting is that you have a metric space. So what does it mean to be a metric space? What does it mean to be a set?
Undefined.
Yeah, exactly. We're not going to go into Zermelo-Frankel right now. We're just going to, these are undefined terms, right? But there are elements of this set, and what this D thing is supposed to give us is distances, okay? So if the distance between x and y, well, first of all, for any 2 points, the distance is non-negative, and distance of x and y equals 0 implies x is equal to y, okay? We want symmetry. And finally, we want triangle inequality. From x to z, getting from x to z should be no worse than going from x to y and then y to z. And now I have to do this. And this. Okay. Good? All right. That's a general metric space. Given a metric space, it induces a topology. So induces a topology by balls, open balls about a point. This is the set of all y. Question?
We use the triangle inequality for the intersection, right? It's open, right?
Well, I'm defining now what open means. We can talk about abstract topology. Maybe I'll prove Furstenberg's version of the infinitude of primes. It's a fun topological argument. But anyway, once you have this map from, so D I should say, D is a function from pairs of points in X to real numbers, and I guess now we know that they're non-negative real numbers. Once you have this, you can pull back the topology from R. So this is all the points. So ball of radius, open ball of radius R about X is the set of all points whose distance, of all points Y, whose distance to X is strictly less than R. Okay, so that gives us a basis for a topology. And what does it mean for a domain to be bounded? Yes, if there exists some R with some R and X in X, with E contained in the ball of radius R about X. Okay, so if you're bounded if you're in some finite set. You are, this is the topology that it induces. Another way, another equivalent definition, I'll leave this as an exercise, is, if the diameter of E, which is the diameter of E, which is the supremum over all distances. If you don't want to think about where this thing's supposed to be centered, so you just look at all distances over X and Y in E, and you look at the supremum of that. If that's finite, well, then just pick some X in E, and it will have distance no larger than whatever that finite thing is. Bless you.
Thank you.
Okay? All right. Let's prove the general Heine-Borel theorem. So general, well, you'll see it's not really Heine-Borel, but I'll call it Heine-Borel anyway. So a subset E of a metric space, let E be an arbitrary subset of a metric space, the following are equivalent. Okay? One is that E is complete and totally bounded. E is complete and totally bounded. So complete we know. Complete is, i.e., every Cauchy sequence. Yep. Every Cauchy sequence xn in E has a limit which is in E. And what does totally bounded mean? Let me slide this up now. Totally bounded is that for any epsilon, you can cover your space by a finite number of balls of radius epsilon. Okay? Totally bounded, for every epsilon, there exist finitely many balls, so x1 through xn of radius epsilon, that cover E. I will give you, I guess I should give you now maybe a counterexample to this definition and why it's not, why it seems like, why is this stronger than bounded? Does anybody know a counterexample? Why this is stronger than bounded? You have to go to a pretty weird space. It's not that weird actually, it's completely natural, but I guess we haven't talked about Hilbert spaces.
I think it may be if you take 0, 1 to the n, or 0, 1 to the natural numbers.
Okay.
Then, r to the natural numbers.
Okay.
Right. Then consider the open ball or the closed ball centered around 0.
Okay.
Bounded, but it won't have this property.
Well,
yeah.
Why not just take the discrete topology on any infinite set?
That's
just
another
discrete metric.
Yeah. So the trivial, I guess, yeah. If you allow the trivial metric, then, but then it's not. So what I'm asking is, what's something that's bounded but not totally bounded?
That's what I'm saying.
Yeah. So the discrete metric, because everything is in a ball of size 1, and then it's not totally bounded because you can't. It's infinite set with the discrete metric, so you're not going to pick everything in a finite number of balls.
Is totally bounded a topological property? Does it depend on the metric that's in this case?
Well, it's being defined in terms of the metric, because so topological means instead of balls, I should just consider opens. But I want to know that for every epsilon, I can cover this set E with open balls of radius epsilon, and using only finitely many balls. So to talk about balls, I have to talk about the metric.
So a different way to phrase the question: if you had a equivalent metric, it would be
very good question. Okay, so we haven't talked about what it means for two metrics to be equivalent, if they differ by constants up above and below. And what do you think?
I think yes.
Why?
Because it's for every epsilon weight.
Exactly. Okay. So this is one criterion. So the following are equivalent. So one condition is that it's complete and totally bounded. When I want you to think about our proof of R being complete, R having the Heine-Borel property. So these two things are certainly satisfied for R. You'll see all the elements of that proof coming up in the proof of this. Property 2 is, I guess I can go either way. All right, let's do Bolzano-Weierstrauss property. Bolzano-Weierstrauss, which says that, did we talk about this?
It's sequentially compacted.
Yeah, so every infinite sequence has a subsequence that converges. Every sequence, arbitrary sequence in E, has convergent subsequence. Convergent subsequence. And of course, by convergent, I mean in E. Has a convergent subsequence in E. And the third equivalent property is compactness. E is compact. We have a topology, so we can speak of open covers. Any open cover has a finite subcover. So in a sense, your question about, this is a purely topological thing, but if you have a metric, then that induces that topology, that's compatible with that topology, then this theorem that 3 implies 1 tells you that this totally boundedness condition is kind of a topological condition, because 3 is a topological condition. But assuming the topology is consistent with the metric.
Does the totally boundedness allow you to drop the part of the Bolzano-Weierstrauss theorem where you need the sequence to be bounded?
Yes. So every sequence in E. So E is complete and totally bounded if and only if every arbitrary sequence of E. And I mean, the same with compactness, right? Compact is, in the real world, compact is closed and bounded. So in the general world, that's basically true, but the reason that it's true is because the real numbers are complete and totally bounded. Or a closed and bounded subset of the real numbers is complete and totally bounded. Yeah. Okay, let's prove these. You can still see everything. Let's prove, so I'll slide it up just a little bit. Let's prove that 1 equals 2. Proof that 1, let's first go in this direction. 1 implies 2. So I'm assuming I'm complete and totally bounded. Let's take a subsequence. Let's take a sequence, be an infinite sequence. I'm trying to prove that it has a convergent subsequence. Okay, but E is totally bounded, so there exists a cover of E by a finite number of balls of radius 1/2. I guess I shouldn't call these xj. They're not related to these. Let's call these yj. And maybe this is n1. N1. Okay? So you cover E by these balls of radius 1/2. At least one of those balls must have infinitely many of the xn's, because the xn, there's a finite list, and the xn's are infinite. So some ball of radius 1/2 about some yj1 contains infinitely many of the original xn's. Cover that ball. Since you can cover all of E, you can cover that ball. Cover this ball of radius 1/2 about yj1 with some finite number, as j goes from 1 to n2, of balls of radius 1/4. About y, so these are y1s, these are y2s. This is y1. This is y1. Y1 is covered, so the ball of radius, you see what I'm doing. You have your set E, you cover it with balls of radius 1/2. You have some infinite set of xn's. Well, one of those balls has infinitely many xn's because there are infinitely many xn's and there's only finitely many balls. So let's take one ball which has infinitely many of those, cover that by balls. So cover E intersect that, I guess, since I don't know that. Cover E intersect that, since I don't know that the ball itself can be covered, but certainly E can be covered. So E intersect this ball, so just this bit of it can be covered by balls of size 1/4. And using only finitely many balls, one of those has infinitely many, so one of those contains infinitely many xn's, and so on. So you're getting balls of smaller and smaller radius that have more and more of these sequences. So the set of xn's that remain, or rather, let's do it like this. So once you have this sequence of balls, or yj's, so we have a ball of size 1/2 about yj1, which contains inside it a ball of size 1/4 about yj2, which contains inside a ball of, and so on, a ball of size 1/2 to the k at yjk in the kth sequence. And some collection of the xn's, some infinite subset of xn's is contained inside each of these balls. So let's take the least n for each, slide this up. You see how to finish it, right? For each k, let n sub k be the least n such that x n k is in this ball of radius 1 over 2 to the k about x, j, k, y, j, k, k. This is getting pretty awful in notation, but it's hopefully pretty obvious otherwise. Yes?
The least distinct point from the previous points, or the least?
I mean, if the sequence, so you're saying yes, yes. Least n greater than nk minus, strictly greater than, let's say, nk minus 1.
Why do we want that condition?
Your subsequence?
So I'm creating a subsequence of the xn's, and I'm going to claim that that subsequence is Cauchy.
Oh no, I meant like the comment that
Oh,
maybe
if-
different.
Well, yeah, I guess if, so if there's if for some reason you have a sequence of balls, if one of the xn's, let's say x1 is the limit of the xn's, then I'm taking x1 infinitely often. The algorithm will continue taking x1, 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 but that's not a subsequence of, you could touch x1 once, let's say you touch root 2 once, and then you wiggle around root 2, converging to root 2.
Oh, so the comment is to take by different is like take different index.
Yes, take
Yeah.
different indices
Okay.
where that happens.
But it could
So-
still be the same one over.
it could
and
be
over.
root 2, yeah. If root 2 appears
Okay.
infinitely often in the sequence, go ahead and take it.
Okay, yeah,
But don't take x1 infinitely often.
yeah.
So I want a genuine subsequence. So that's the increasing. And then I gave away the ending. This is a Cauchy sequence because they're all inside a ball of radius 1 over 2 to the k. So that's how far you need to go out. So this is a Cauchy sequence. This is a Cauchy sequence. So we use the total boundedness at every stage because there are finitely many balls of an arbitrarily small epsilon, which we're taking to be 1 over 2 to the k's. Now we're using the completeness. This subsequence is a Cauchy sequence and hence converges. So this subsequence of x and k's converges to some x in E because E is assumed to be complete. Okay? What does this argument mimic when we were proving completeness of the real numbers?
The closing bounding question.
There was a step in that.
Oh, when we were looking at K-cell things?
Yes, exactly. Right? How did we prove that the interval negative a to a, the closed interval negative a to a is compact, or to the n, if we're doing exactly. We were chopping up into balls, using the finiteness of those balls to say there's infinitely many in one of those balls, or cubes, or whatever it was we were using, and zooming in. Okay? So that's what I meant by that argument is a general argument, even though it's only an Rn argument. The idea is proves the general statement. Okay. Any questions on the proof of 1 implies 2? You zoom in on balls. Every stage you have to have infinitely many because there's only finitely many balls by total completeness, total boundedness.
So sequence convergence doesn't necessarily need a metric space.
Sequential convergence. So this is, so to define Cauchy,
Right, you would need one.
I need a metric because,
Right,
yeah.
you don't-
But so this is every, well, so what do you mean by converges then?
I mean that around the accumulation point for any ball, there's a point that's not equal to the accumulation.
So we can do it topologically for every
So-
open.
So is there, my question is there like a Heine-Borel for that situation where you don't have a metric space at all?
So yes and no. Let me get through this, but let's talk about that because that's there's some subtleties if you drop metric. Okay. Can you see? So that was 1 implies 2. Any questions on 1 implies 2? Let me put back the statement. Now let's prove. What do I want to prove next? How about 2 implies 1? Since they're all equivalent. So we've proved 1 implies 2. Now we're going to prove 2 implies 1. So proof that 2 implies 1.
Seems inefficient.
Yeah. Should we do 2 implies 3 and then 3
Yes,
implies 1?
Three.
That might get difficult.
Yes.
You'll see why I'm going in this order.
Okay.
This makes things slightly slicker. You can, obviously, they're all equivalent, but you'll see that it'll be useful. I will do 2 implies 3 by using by using 1. So first I want to prove that 2 implies 1, and then 2 implies 3, we'll say, well, I might as well assume 1 and 2 to prove 3. That'll make things a little easier. Okay, so now I'm assuming that every sequence has a convergent subsequence. I need to prove both completeness and total boundedness. Okay. So the first thing I want to prove, so one way of proving this is to prove the contrapositive. So not 1. What we'll really prove is not 1 implies not 2. Okay. So if so let's say there's a Cauchy sequence. So let's say completeness fails. If there exists a Cauchy sequence with no limit in E, then there's not a convergent subsequence, because if there was a convergent subsequence, then the Cauchy sequence would converge to that limit point. That's clear, right? Then there is no convergent subsequence. All right. So that's that completeness is necessary. Why is total boundedness necessary? So if E is not totally bounded, there exists some epsilon such that there is no finite, there does not exist a finite epsilon ball cover of E. So what's your sequence?
Take 1 point in each point.
Take 1 point in each ball. Let me just be a little bit more careful. Let's do it a little bit more carefully, which is to do it sequentially. So you take an x1 in E, okay? And then sequentially, what you'll do is take any x1 in E and iteratively take any xn in E, take away the union of all of the epsilon balls about the previous xj, as j goes from 1 to n minus 1. Okay? So these balls cannot ever cover E in finite time, and hence there is such an xn. This set is non-empty because if it was empty, then I would have covered in finite time of size using epsilon balls the set E. So there is such a sequence, and these points all have distance at least epsilon over 2 from each other, or even epsilon. All xn have distance at least, let's say, epsilon from each other, so they can't have a convergent subsequence. Do I need to spell that out? I think it's clear. Distance of xn to xm is always at least epsilon. Questions?
This may be a bit silly, but it's not completely obvious to me that there's a rigorous pointwise whatever proof of that if you have open balls of size 1 over 2 or epsilon or whatever, then if you take E, remove those, then there exists a open ball of size epsilon which is not intersecting with these.
So let's look again at the argument. So you start with let's draw a picture. So here's E. I take some point. Sorry. Okay, here's E. I take some point x1. And I remove the ball of size, so here's a ball of size epsilon around x1. That can't be empty. Otherwise, I will have covered E infinitely many epsilon balls, and I'm assuming it's not possible. There does not exist any finite epsilon ball cover. Okay, so then I take a point x2, anywhere outside of there. I take an epsilon ball around that. Those two balls together can't cover E. and so on.
The balls don't need to be distributed.
I never said the balls are disjoint. So if this is x3, here's the radius epsilon ball there.
Okay.
The point is x3 is not in the epsilon ball around x2, and that's why the distance is at least epsilon.
Okay.
Maybe I want an equal sign there, because this is it. You know it. Okay? Good.
But I think if xn is in the rest of the E, so if it's in the rest of the E, it still can be very close, right?
Well, it can be very close. So I can put an x4 here, but then I have an epsilon ball, and I'm not allowed to take any more points in that epsilon ball. So I can take another point there, and then I have an epsilon ball, and I can take another point there, and that's an epsilon ball. That's it. I'm out of room. I have to start putting more epsilon balls here, and so on. And this process has to go on forever by the assumption that E has no finite subcover, has no finite epsilon ball cover. So that's the creation of a set of xn's, each of which differ from one another by epsilon. So if they had a limit, whatever that limit is, well, once you get one guy near that limit, nobody else will be near that limit again. Okay. Let's prove, all right, so we proved the equivalence of 1 and 2. How do I do this? Can I fold this? Is everyone happy with 2 implies 1? Because not 1 implies not 2. Let me fold this over so we can still look at the statements. Okay, let's prove that 3 implies 2. That's this direction. And then we'll be almost done. All right. Compactness implies sequential compactness. Okay. So let xn be an arbitrary sequence in E. I want to prove that it has a convergent subsequence. So here's what I want to do. First, I want to cover E. It's the same argument. Oh, by the way, in this argument, how is this argument similar to what we proved in, well, I guess we didn't talk about sequential compactness when we were proving Rn. So there's no parallel because we went straight to compactness and in terms of complete and totally boundedness. Okay. Right. So let's cover E by balls of radius 1/2. Arbitrary balls, but then any arbitrary cover has a finite subcover.
Are they around the points of the sequence?
No, sorry. Wait a second. Yes. What am I trying to say? No, I'm just saying an arbitrary cover has a finite subcover. It's the same proof as before. You take E, you cover it by a finite number of radius 1/2 balls, and one of them has infinitely many. Since it's the same, I mean, what we used in totally boundedness, we can use in compactness. It's the same proof. So I look at balls of radius 1/2. The balls of radius 1/2 about every point in E cover E, which means there's a finite subcover.
So compactness implies total boundedness.
That's where that'll be the last step. Yes, but compactness, yes, implies totally boundedness just trivially. Okay, and totally boundedness. So this will create a Cauchy sequence, and hence, but that sequence converges. Okay, so same argument. So continue as before. Okay. And finally, 2 implies 3. So the proof that 2 implies 3. You can still see everything. And we're going to use 1 plus 2 because 2 implies 1. So I can throw in 1 as I wish.
I think when we did 1 implies 2, we also used completeness toward
Yeah,
the
you-
end of the argument.
You just get a Cauchy sequence here, right? For 3 implies 2?
Every open cover has a finite subcover. We get a Cauchy sequence.
That doesn't have to converge.
Yeah, maybe I want to do 1 and 2 implies 3 first.
Okay.
To know that 3 implies, no, what am I trying to say? What am I trying to say? I'm trying to rush through this to get to better stuff.
So, using that in every compact set, every sequence has a subsequence that converges.
Yes, exactly. So we've
We have
created our
Cauchy
Cauchy sequence.
We can just prove completeness of compact sets, right?
Is that a true statement?
Yeah.
Well, that's
compact
what-
sets are complete. We can prove-
That's 3 implies 1. Yeah, I guess I can prove 3 implies 1, which then implies 2. But that's,
Yes.
then we're done. Okay, so the total boundedness is obvious.
Yeah.
Because if this is take the set of all epsilon balls, that's a cover, so it has a finite subcover. So for every epsilon, there is a finite subcover. The completeness from compactness, I mean, that's what we proved for the real numbers. And that argument is the same. I mean, this is how you get the subsequence. This is how you get the convergent subsequence, is you get this series of points. It's exactly what we did before. I mean, that's what I mean by continue as before. All I wrote in my notes is continue as before, but the continue as before is what we did to prove the completeness of the, what did we call those? Cubes, whatever. Is you keep subdividing, and you keep subdividing until you zero in on the limit point. There's your limit point. Okay?
Oh, we get like a nested sequence of compact sets.
Well, yes, because they're all subsets of E. So that's your limit point. Okay? We can return to that if you're not happy with it. I'll try to give you a better argument, but it certainly seemed to be obvious, and now I would like to have a better argument. Let's come back to that. So 2 implies 3, but I'm allowed to use 1. So so I'm trying to prove compactness. So assume E is covered by some arbitrary collection of opens, A in some indexing set, capital A. Okay? I want to know that I have a finite subcover. So here's what we're going to do. So my claim is that there exists some epsilon so that every ball of radius epsilon about a point intersecting E with a non-empty intersection is in one of these, is in at least one of these B alphas. I shouldn't really call them B's, they're not balls, they're just opens. So let's call them O alphas. Okay, so one more time. Here's E. If I have some ball of radius epsilon about X, so here's my ball of radius epsilon about X, if it has non-zero intersection with E, non-empty intersection with E, then this ball is already contained inside some open. Okay, that's my claim. Is the statement clear?
There exists an epsilon.
My claim is that there is some epsilon, there exists an epsilon, so that for that epsilon, every epsilon ball that intersects E non-trivially is already contained in some O. Okay.
Lebesgue number?
Sorry?
Is this the Lebesgue number?
Yes.
Okay.
So, I mean, that's what we're proving. We haven't proved it yet. So if not, then for every epsilon, there does not exist this property. So for every epsilon, or let's make a sequence of epsilon. So for every n, for every n, there exists a ball, Bn, which is a ball of radius 1 over 2 to the n, about some xn, which intersects E, not in non-empty, and Bn is not contained in any O alpha, right? That's the negation of the statement that there exists some epsilon. So if not, then I'll choose epsilons to be 1 over 2 to the n's, and I can always find.
Let's just, before that, you say every b epsilon x, is that means for every x, right? Every x in E. Or
Yes. So
x in E or
yeah,
x
let's take
in
x in E. Well, I don't care about. I mean, I think this will be true in general, but let's take x in E because of what I'm about to say. I do want x in E. So this was kind of a misleading picture.
Yes.
I do want x in E, and then a ball of radius epsilon about x. Okay. And here again, let's take x in E. I do want x in E for this argument. Okay.
When you say is, the subject is ball radius epsilon around E?
Yes, every ball, thank you. For every, I guess what I mean is, for every x in E such that the ball of radius epsilon about x intersects in E non-trivially, then this ball of radius epsilon about x is contained in O alpha for some alpha in the indexing set. That's a better way of saying it. Okay?
Can you just go through the modifiers one by one?
Yes.
Stating?
So the claim is there is some epsilon. So that anytime I have a point x in E, which for which the ball of radius x is contained in for which the intersection is non-empty, then now let me think. I'm changing the argument on the fly. I mean, this is trivially true because x is in E.
Yes, it's always not empty.
So what I really mean is what I really mean is what I said before, but all I will use is the ones that are in E. So any epsilon ball, all I really want is that for every x in E, the epsilon ball about x is contained in some O alpha. Okay? If that's not true, then I can find this sequence of balls, sequence of xn's in E, with balls of size 1 over 2 to the n, because it's not true, so for every epsilon this fails. There does not exist an epsilon for which this holds. For every epsilon this fails, that means I can take epsilons to be the sequence 1 over 2 to the n, and I'll find a sequence of xn's, which are in E, so they intersect non-trivially, but this is not contained, this radius 1 over 2 to the n ball is not contained in any O alpha. Okay? So what does that mean? The xn's are a sequence, an infinite sequence in E. And I'm assuming two. I'm assuming I'm assuming a sequential compactness. So there is a subsequence, but there exists a subsequence of the xn's, xnj, with x and j converging to x in E. What does that mean?
Like all but finitely many are contained in some small ball around X.
Yes, right? So so x is in, the point is but, you can still see, but x is in E, so x is in some O alpha, which means there's a ball of radius epsilon around x that's in some O alpha, which means there exists a ball of radius epsilon about this limit point x, which is in some O alpha. And all of these balls of sufficiently small radius sit inside this ball of fixed radius epsilon. Okay, so that's the contradiction. I guess I don't need a contradiction. If it's not true, then do this until it is true. So some 1 over 2 to the n ball and all the future balls are contained in this subsequence are contained in this O alpha end of claim. Okay? So once we know, so we proved the claim, so this proves the claim. So once we know that there is such a ball, there is such an epsilon, so that every epsilon ball has this property. Now we're done because
we can assume totally bounded because we have 1 and 2 are equivalent.
Yes, exactly. We're going to use the total boundedness. Okay? So once we have this epsilon, that means that E can be covered by finitely many of these special epsilon balls, this epsilon, but each one is in some O epsilon, each in some O alpha. So those are only the finitely many alphas that you need to cover all of the question.
How do we know that they're the epsilon balls we want? Like, it's true that every point has an epsilon ball around it, which is contained in an O alpha. Maybe I'm saying something silly.
So let's look again.
Yeah.
So there exists some epsilon, so that every epsilon ball around E is contained in some O alpha.
Okay, yeah, I'm satisfied. Sorry.
Yep. So now take the epsilon balls that you need to cover, the finitely many epsilon balls that you need to cover E, which is what totally boundedness guarantees. Then each one is in some O alpha. Those are the O alphas you need to keep for your finite subcover. That's a finite subcover. Finite subcover. Okay. All right. And that is that 3 implies 2, and okay, so everybody implies everybody.
How would we get rid of the contradiction in this last step? Seems like it was kind of important to pick the xn's, right?
In the last step.
Yeah, you said, like,
in the proof of the claim? Or the finish?
In the proof of the claim.
Yes.
It seems like it was important to have that contradiction, like the contradictory assumption, to get the sequence that we needed.
Well, it's not, so what I'm saying is, assume it's not true, assume we haven't succeeded yet in finding the O alpha.
Right.
Then continue until you find the O alpha. Now, I guess it really is useful to have, I guess we really do want to assume that the contradiction.
Yeah.
This really is a proof by contradiction. It's not a finite algorithm, because I need to get the subsequence, which means I need infinitely many terms of this contradiction.
That's annoying.
Yeah. Yeah.
Did you do contrapositive?
I mean, in some sense, they're all equivalent, right? So we can dissect this up the wazoo, but yeah, you're right. It's not a finite process. What I said before is not right. It's not a finite process because we really are using the subsequence has a limit.
Yeah.
We've used infinitely many of these contradictions. Now that limit is in some O epsilon, so there's a ball around it because this is open, and there you go. Okay, any questions on general Heine-Borel? So again, this is kind of review. Yeah. Question?
Does if E satisfies 1, does it imply that E is at most uncountable?
If E satisfies 1,
What is it?
What is
Does
the
it-
most uncountable?
That there exists a surjective map from the reals into.
At most cardinality of R, right?
Well, I mean, for one thing, don't
I don't know how big these
ask
balls-
you to assume that reals are the smallest uncountable thing anyway. That's
Let's
it doesn't
assume this.
follow from.
Yeah, we're not talking about continuum hypothesis, but I don't even know what the cardinality of this is.
I didn't think that it was just a like, that it was a quick proof from 1 to it's at most uncountable. I was just wondering if it was just ended up being true by some hypothesis or something.
I don't see why, because if I have a set of cardinality larger than the continuum, if a ball of radius epsilon about a point in a metric could also have that cardinality.
Right.
So just because you have finitely many of them doesn't mean that the cardinality is at most the cardinality of the continuum.
Sure, I don't see anything wrong with it yet, right? But I was just wondering if
Oh, if it's true. No, I don't think it's true. I think there are things that have larger cardinalities, although I'd have to think to come up with
Like,
an example.
why is there something, they don't know if there's something between cardinality Z and cardinality R, like,
Right.
they don't know what's like,
Well, we know that it is up to you to decide whether you want there to be one or not.
yeah.
Right? That's the independence of the continuum hypothesis from axiom of choice and Zermelo-Frankel and all the other good stuff. Question?
I don't know if you
So
wanted to
you
do
just
this
stick
next time, but do we have compactness implies completeness?
Right. This was this step that I said continue as before. In the interest of time, let me try to give you so I'll put a star next to this to give you a better argument. Okay. Let's do, can we continue?
Oh, I have.
More
The
questions?
The question I
More
meant to
discussion?
ask
Yes?
was, does this imply that X is separable? Or E is separable?
So we haven't talked about separability. Does everybody know what separability is? What's separability?
It's a countable dense subset.
Countable dense subset. So again,
I don't compact implies separable.
That's
Um,
right.
yes,
Metric spaces at least.
in metric
Metric
spaces.
spaces.
Yep. But I haven't proved that, so.
But
Take the epsilons to be 1/2 to the n, you get finitely many of them for each n, and that'll be your compact countable set.
It
Or
won't
dense
nec-
countable set.
It won't necessarily have, just picking.
you can do a greedy algorithm.
In the
Okay,
interest
okay,
of
got it.
trying to get through, I love this discussion. Let's continue it offline, if you don't mind. Because I do want to get through the measure theory. That was supposed to be a review of the metric, general Heine-Borel. This is all supposed to be review, but review from a general abstract point of view. Okay, we talked about measure. The naive notion of measure fails, so we're going to restrict to, we're going to build up measures from pre-measures and exterior measures and so on. So let's just recall, what does it mean for, so x a mu 0 is a pre-measure. This is again just recalling definitions, is a pre-measure if
A is an algebra.
yes, A is an algebra, not a sigma algebra, but just an algebra, or a sigma finite, some people will say, sigma finite algebra, which means,
You have finite union, intersection.
yes, closed under complement and finite unions and intersections.
Wait, does the empty set have to be in there? Or-
Yeah, and you want to put the empty set and the whole, and let's say non-empty at least. If it's non-empty, then the empty set's in there. So that's what it means to be an algebra, and the triplet is a pre-measure if mu 0 is a pre-measure space, I should say. Is a pre-measure space is something with an algebra and a pre-measure, and mu 0 is a pre-measure, which again means
It is defined on the algebra and is countably additive.
and countably additive. And countably, not finitely, but countably additive. In other words, it is a measure, it's not mu0's fault that it's not a measure. It's A's fault that it's not a measure. Countably additive, i.e., if it so happens that you have a bunch of sets in A and their disjoint union is also in A. So this is the thing that is not guaranteed, and this is a countable disjoint union, then mu0 of this countable disjoint union is equal to the sum of mu0 of the EJs. Okay? So that's a general pre-measure. The way we got a general pre-measure in our study of the big measure on the reals was through rectangles or cubes or whatever. That was our kind of algebra and pre-measure, and the notion of pre-measure was then, for rectangles, just the length. And here's the theorem. So this is the extension theorem. Oh, I have to define exterior measure. We know what an exterior measure is. Countably subadditive on the entire power set, on any subset. So the theorem is if xa mu0 is a pre-measure, then x mu star is an exterior measure, outer measure, exterior measure, where mu star of any set, any subset of x is defined to be this is a comma. So x comma mu star, I'm defining mu star below. And once I define mu star, x comma mu star will be an exterior measure space. And mu star will be an exterior measure, where this is the infimum over all covers of EJ in your finite, sigma finite algebra of the sum of mu0 of the EJs. So the infimum over all these sums, over all covers, with sets taken in A, that will be an exterior measure. Moreover, so this is part one. Part two, moreover, for every E in A, the exterior measure of E matches what it would have been if you hadn't done this. Okay? All right. What do we need for a pre-measure? Pre-measure needs to give the empty set measure 0. You can cover it by the empty set, and empty sum is 0. Okay? So if E1 is contained in E2, then any A cover of E1 is an A cover of E2, so the infimum is at most the infimum. Okay? A cover of E2 is 1 of E1, which implies monotonicity. I'm checking the axioms of being an exterior measure. Yes. So we have the empty set as measure 0, we have monotonicity, and the last thing we need, countable subadditivity. Yeah, countable subadditivity. So if we have a bunch of sets, arbitrary sets EJ, and their total union is some set E, not disjoint, but countable. So this is arbitrary. It's trivial unless the statement I'm about to make is trivial unless the measure of each of these things is finite. Assume each of these has finite exterior measure. Then what are we going to do? You run the standard algorithm. I want to prove that, what am I trying to prove? That the measure of E is at most the sum of the exterior measures of the EJ. Everything here is arbitrary. Nobody's here is measurable.
Would you make them disjoint first?
You could. You don't even have to. Yeah, so what is the definition of mu star of each of these EJs? Each EJ has a cover by, what am I going to call things in A? I guess regular A's, A, K, J, with A, K, J's in A, such that, by the definition of what mu star is, such that the sum of the mu zeros of the A, K, J's is at worst exactly. So the measure of EJ plus epsilon over 2 to the J, something like that. Again, this was exactly the same argument we used in the real case. I'm just showing you that it works completely. I'm reviewing that by showing you that it works in complete generality. So E itself is covered by the union over all J and over all K of these AJKs. And so the exterior measure of E is bounded by the exterior measures by since it's an infimum, it's bounded by the sum over J and a sum over K of the pre-measures of all these AJs, AJKs. But each AJK, so this is a sum over K, let's be careful about the indices. So each of these is bounded by the sum of so this is sum over J, the exterior measure of EJ plus epsilon. Same argument, goes through just as before. So that's the countable subadditivity, send epsilon to 0. Any questions on why this is a pre-measure? I still have to prove the moreover. Yes?
Are the covers for EJ like arbitrary unions or?
Arbitrary, yep. Definition is arbitrary, not disjoint.
But it's countable, right?
Countable,
Okay.
yeah, arbitrary countable,
Okay.
yes. Because I'm going to use the countable and countable is countable. So this is a countable cover of E. Okay, so again, this was the same argument we did with the reals. It works in general. Here's the general theorem, the general extension theorem. And the last thing I have to prove is the moreover. So let me slide up. So to prove the moreover, the obvious observation is this inequality, because E is a cover of itself. If E is, so this is if E is in the algebra to begin with, this is obvious. Let's go in the other direction. Why can't it somehow get smaller by some cover? Okay, so let E be covered by some AJ in A, and set EK to be E intersect AK, take away the union of all the previous AKs. So this is the disjointed argument. I'm running out of room. Let me put it here. Set EK. Now I have to scroll up.
Scroll.
That's the thing you can't do on Blackboard. You can't scroll up. Okay.
We 705, we can scroll.
E intersect AK, take away the union of all the previous AJs. Let's parse this. The E is in A. The AKs are in A. This is a finite union. This is a complement. This is an intersection. All of these things, so this is in A. I have a right to say that this has a measure. This is in A. And so these are all disjoint things that add up to, so the measure, by the fact that mu 0 is a pre-measure, the measure of E is at most the measure of these disjoint EKs. Okay? And that is equal to, let's see if I can finish it on this line, that is equal to the sum of the EKs, because mu 0 is a pre-measure, so here I'm using that disjoint sets EK add up. So this is mu 0, you can't see, mu 0 of EK. And this is true for any A cover. Okay? And this is true for any A cover. So it's true for the infimum of the A covers. So the A covers can't get below the measure. Which implies mu star can't get below the measure either.
I guess we started with AJ as our cover. So do we ultimately want to say?
Yes, and this is equal to mu 0 of the AKs. Thank you. Because, let me slide this up. So because of the construction of this sum. So finite sums of this, the measure of each of these EKs, why am I running out of room? Yeah, good. So if you add up the EKs from 1 to K, that gets you AK, intersect B. So these things are adding up to these things.
Less than or equal to? Because you might have overlap in the AKs? Exactly.
Okay. So what that means is any cover has a sum which is at least mu 0. So the infimum over all covers is at least mu 0, and the infimum over all covers is mu star. So mu star is at least mu 0, and it's also at most mu 0. So it's equal to mu 0. Okay. Any questions on the extension from pre-measures to exterior measures? Some people call these inner measures, inner to outer measures. Let me put the theorem back up. So this is what we did this is exactly what we did when we had rectangles and we argued with rectangles, but really what we were arguing was pre-measures.
Oh, I have a question.
Please.
How do the rectangles form in algebra?
Right, so we didn't prove it rigorously, but if you look at rectangles, so we want the algebra generated by rectangles. So if you take the intersection, the point geometrically, let me make it here. The point geometrically is that when I have a finite number of rectangles, it decomposes into a finite number of, so if I have complements of rectangles, I can make open rectangles, and I can also make rectangles that are infinitely thin. And so this decomposes into, so this is something that's in the algebra, because it's a countable, it's an intersection of a finite number of rectangles. So a finite set of rectangles will only ever break up into things that are complements and intersections and unions of finite many rectangles.
Including a rectangle could go to infinity in this system.
Well, right. So the complement of a rectangle will be an infinitely large thing. Yeah, everything outside of this rectangle is is a set that's in the algebra. Okay? And that has infinite pre-measure, and that's okay. Question?
Could you repeat one more time what was the analogy between these and like the R case?
The analogy between these and RKs.
And the pre-measure and exterior.
So all I'm saying is the way that we constructed exterior measure when we were doing this just for RD, for the real space, was exactly the same thing, and we were using, you can do this with cubes or with open sets or with, you have any number of notions of pre-measure, balls, whatever. But you, in the end, it's something completely general. It's a general statement about pre-measures extending to exterior measures. So this is the abstract version of the same thing that we did for RD. Okay? And now let's do almost the same thing, but these are, there's no, I never said this has a topology, I never said this had a metric. So we can't take open, our definition, the way that we finished this before, so recall, in RD, the finish was to say that E is open, E as open, is measurable if for every epsilon there exists an open cover with exterior measure O take away E at most epsilon. But now we don't even have a topology. We could give ourselves a topology, we could just assume we're on a metric space, the metric induces topology, and then work from that. There's something even slicker, which is the Carathodory notion of measurability. So definition, given an exterior measure space, measure space X mu star, a set E is called Carathodory measurable. A set E is Carathodory measurable, or mu star measurable if you need to specify if there are several exterior measures floating around for some reason, but let's not do that to ourselves. Given an exterior measure space, a set E is Carathodory measurable if, here's what you want to do, it's kind of like a separability condition. Thank you. In fact, I don't need this anymore. If for every other set A in X, the exterior measure of A can be obtained from taking the exterior measure of A intersect E and adding that to the exterior measure of A intersect E complement. This is the substitute for the real notion of measurability, the Lebesgue notion of measurability, which we have trouble extending in complete generality because it assumes a topology.
How does the real one break down into this?
You will see, so there's an exercise. In fact, I think I haven't posted the exercises yet. Okay, so I'm going to post the exercise that this notion, in the case of RD, implies this notion, or in the case of a topology, implies the open notion. And if you have a topology, then they're equivalent. Okay, so here's a little lemma to get us started in the Carathodory extension theorem. So if you have a pre-measure, and mu star is the extension, as in the previous theorem, then what I want to say is every E in A is Carathodory measurable, or just, he has a long last name, I sympathize, so I'll just say measurable. In this notion of measurability. So again, we had our finite, sigma finite algebra. We made this new notion of measurability, which is about arbitrary subsets of X. And now I'm saying if you were in your pre-algebra, in your algebra, not sigma algebra, and mu star is the extension, then that set is indeed measurable. It's not obvious, because you're going to try to you need an equality of exterior measures across arbitrary subsets of X. Is that clear? So let's prove this. We can do this. Okay, so let E be in A and A arbitrary. This is maybe awful notation, but it's too late now, I've written it. Okay, the upper bound, so this follows from subadditivity. You can't see, so I'll slide it up. Okay, so this just follows from subadditivity, which we proved because we proved that mu star is an exterior measure. So we need to go in the other direction. So cover A by some EJ in A with the property that you haven't overdone it. So the sum of the mu 0 EJs is at most the eventual exterior measure of your set A plus epsilon. Now each of these, by the additivity, in fact sigma additivity of mu 0, each of these is equal to the sum, so this is a sum over J, of mu 0 of EJ intersect E plus mu 0 of EJ intersect E complement. These are two disjoint sets. They add up to EJ. Mu 0 is equal on each of these. Again, I should have said from the beginning, assume everything is finite. Assume this mu star is finite, otherwise there's nothing to prove. This covers A intersect E, and this covers, so what I mean is the union over all of these. The union over J of these things, covers A intersect E. These cover A intersect E complement. And so this is an upper bound for mu star of A intersect E. And this is an upper bound for mu star of A intersect E complement. So that's a lower bound with an epsilon. And we're done. So far, so good? Okay, so that's the lemma, that these E's are indeed measurable with this notion. And now we can prove, although maybe we'll just have time to state, the Carathodory extension theorem. Did I already state this before? Carathodory. I can't remember if I did or not.
I don't think so.
Okay, good, then it's new. If you have an exterior measure is an outer measure, then let's call this the set M, which is the set of E in X that are measurable, Carathodory measurable, is a sigma algebra, not just an algebra, but a sigma algebra. Of course, it contains, so this is a general theorem. I'm not assuming any longer that mu 0 is generated by some pre-algebra. But if it was generated by some pre-algebra, we would know that M contains the pre-algebra, the sigma finite algebra. Okay? This M is a sigma algebra. And, of course, this is part 1 and part 2 all together now. Restricted, exactly. The exterior measure, so mu of E defined to be the exterior measure, well, so what I mean is mu defined to be the exterior measure restricted to this is a measure. In other words, it's countably additive, not subadditive. Only thing we're missing is countably additive, not subadditive. All right. I think we have time. Proof of one. Proof of one. Maybe I'll slide this up, start a new page. Okay, proof of one. So first of all, if E is in M, if E is measurable, again, what does measurable mean? This is why I want to be able to do this up and down. Measurable means that for any set, the measure of A is equal to the measure of A intersect E plus the measure of A intersect complement, E complement. The definition is already symmetric. So if E is in M, then E complement is in M, because definition is symmetric. So that's nice. Remember before we had to find closed subsets contained inside of it so that the complement would, right? That was a little annoying. So this is slightly nicer. Now I want to know about countable unions. So, okay, the empty set is in there, the whole set is in there. Okay, so first let me claim that if if E1 and E2, let me get finite unions first. E1 and E2 are in M, implies that E1 union E2 is in M. Because even that takes proof now. Okay, so let's prove it. That might be all we have time for, but that's okay. So that's my first claim. So let's look at, so let A be an X, arbitrary. This is a simple subdivision. So here's A, and here's E, E1, and here's E2. So I have to make sure I get a little bit of everything. That shouldn't be too hard of a Venn diagram. They get a little bit of everything? Yes. Because I have A intersect E1 but not E2, A intersect E2 but not E1, A intersect both, A intersect neither. Good. The measure of A intersect E1 and E2, let's see, let's try to get this clean. So, I know that the measure of A, because E1 is measurable, the measure of A can be decomposed into the measure of A intersect E1 plus the exterior measure of A intersect E1 complement. That's because E1 is measurable, and that was the definition of measurability. Now this, I'm going to break up, so this is this bit, A intersect E1. I'll break up as the measure of A intersect E1 intersect E2 plus the measure of A intersect E1 intersect E2 complement. Thank you. Okay, so I just broke up this A intersect E1 into A intersect E1 intersect E2 complement and A intersect E1 intersect E2. Why is that true? Why is it true that mu star of these adds up if the sets are disjoint and add up? Because E2 is measurable. Okay, so here I'm using so far that E2 is measurable to break up this into these two pieces. And similarly, I'm going to break up this, the complement, A intersect E1 complement, into two pieces, again using the fact that E2 is measurable. So this is the measure. This is a simple argument, right? E1 complement intersect E2 plus the measure of A intersect E1 complement intersect E2 complement. Now, what's the observation? I don't know. I'm trying to prove that E1 union E2, I'm trying to prove that this thing is measurable. But all I know is subadditivity. So what are these three pieces? This is A intersect. So there's an A intersect E1 complement E2 complement. That's this bit. So this is also A intersect E1 union E2 complement. That's just an equality. But these three pieces together add up to A intersect E1 union E2. And so this is plus A intersect E1 union E2 complement. So I'm going to group these three together. And they are disjoint things that add up to whose union is this. So by subadditivity, I have this inequality. Okay? But I need an equality, not an inequality. How about the other inequality? It's always true. It's still subadditivity. And mu star of A is at most mu star of A intersect E1 union E2